this video, we will be discussing about maximum number of k divisible components. There is an undirected tree with n nodes labeled from 0 to n minus 1. You are given an integer n and a 2D integer array edges of length n minus 1, where edges of I equals to ai bi indicates that there is an edge between the nodes ai and bi in the tree. You are also given a zero indexed integer array values of length n, where values of I is the value associated with the ith node and an integer k. A valid split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k, where the value of a connected component is the sum of the values of its nodes. Return the maximum number of components in any valid split. The constraints that are given to us are that the number of nodes can at max be 3 into 10 to the power 4, right? And it is also given that the sum of values is divisible by k, right? So what they are saying is that in the input, we are given few of the items. First one is n, which denotes the number of nodes in our undirected tree, right? Remember, it is an undirected tree. Then we are given a 2D array, that is edges, which denotes that in this 0 and 1, there is an edge between node 0 and node 1, which is an undirected edge, right? Then we have a values array, which denotes that, okay, at the node 0, the value is 3, at node 1, value is 0, at node 2, value is 6, and so on, right? And then we are given another integer k, right? Now let's see what we need to do. So before that, with this edges array, let's try to build the tree that is given to us, right? So first we are given that there is an edge between node 0 and node 1, right? So this is node 0 and this is node 1, right? This is 0, this is 1, and there is an edge between these two, right? Then next we have an edge between node 0 and node 2, right? So this, let's consider as node 2, there is an edge between them, right? Then the next is that there is an edge between node 1 and 3. So let's create a node 3, right? Then we have an edge between node 1 and node 4. So we have a node 4 over here, and there is an edge between these two, right? Next is an edge between node 2 and node 5. So let's create a node 5 over here, right? Next we have a edge between node 2 and 6. So we will create a node 6 over here, right? So this is what our undirected tree looks like with the help of these edges. Then what are the values? If I give the indices, so 0, 1, 2, 3, 4, 5, 6, right? So for the 0th node, the value is 3, right? I'll write here. For 0th node, it is 3. For node 1, it is 0. For node 2, it is 6. For node 3, it is 1. For node 4, it is 5. For node 5, it is 2. And for node 6, it is 1. So these are the values. Now what we need to do is that we need to split this undirected tree into some number of components by removing some edges, such that in each component, whatever is the sum of the nodes values, that is divisible by k, right? So if I consider this entire tree, right now this is one component, right? All the nodes are connected with each other. This is one component. So now here, if I do the sum of all the values, right? So this is 1 plus 2, 3, 3 plus 6, 9, 9 plus 3, 12, 12 plus 0, 12, 12 plus 5, 17, and 17 plus 1, 18, right? So it is 18. 18 is divisible by 3, right? So this is also one of the valid component where the sum of the values of all the nodes is divisible by k, right? But what you need to do is you need to maximize these number of components, right? So see, if I remove this edge, then this will be one component and this will be one component, right? So now if you will see, this will be 6 plus 1, 7, and 7 plus 2, 9. So this is divisible by k. This is a valid component. Then here 3 plus 0, 3, 3 plus 5, 8, and 8 plus 1, 9. So this is also a valid component, right? So now our number of components became 2, right? So we need to maximize the number of components, right? So now it is given to us in the question that the initial values, basically the values of this entire tree, are always divisible by k, right? So if I find out a component in my tree which is divisible by k, then whatever is the remaining part, that will also be divisible by k. Understood, right? Because the entire tree values are divisible by k, right? So if I am taking some part of it out which is divisible by k, then the remaining part will also be divisible by k, right? That is what I'm saying. So now how can we solve this? So see, First of all, whenever there is a valid component, we are having some nodes in it and we are considering the values of those nodes, right? So let's forget about edges for now, right? If we forget about edges, so see, if I say that let's consider this particular node and let us suppose that its value was 5, right? So now this node alone, can it be a valid component? No, right? Because its value is 5, which is not divisible by k, right? So this node alone cannot be a valid component, right? So this node's value will either be added with this neighbor, or with this neighbor, right? Basically, this node 2 is having three neighbors. It is connected to three other nodes, which is node 0, node 5, and node 6, right? So if this node alone is not able to create a valid component, then it will either create a valid component with this node, or with this node, or with this node, right? But how do we identify that if there was 5 here and it was not able to create a valid component in itself, then with which of its neighbor is it going to combine? So see, we cannot try out all the possible combinations, right? Because it will increase our time complexity, right? So how do we decide that with which node should I add this node? So see, instead of considering this node first, what we can do is that we can consider those nodes first which are having only one neighbor, right? So those are nothing but the leaf nodes, right? If you see, for all the leaf nodes, they are having only one neighbor, right? So here we know that if this particular node alone is not able to create a valid component, then it will obviously create a valid component with this particular node, right? Now, this particular node might further create a valid component with its neighbor, but for this, we are sure that if alone it is not able to, then it will kind of impact this particular neighbor. It will give its value to this neighbor. So basically, if you see what I said, that we will consider all the leaf nodes first, basically the nodes which are having only one neighbor. And how are you going to identify that what are all the nodes which are having only one neighbor, which are having only one edges we are given, right? So what we can do is that we can create an in degree vector or an array, right? In degree basically denotes that how many edges does this particular node have which are coming towards it. But since this is an undirected, so whatever edges this particular node will be having, we will count all of them in our in degree, right? So whichever node will be having its in degree as 1, that will be a leaf node, and we will consider those nodes first, right? So here this was having its in degree as 1, right? So we saw that its value is 1. Now here it is not divisible by k. Then that means this will contribute to node 2 in forming a valid component, right? So what we can do is that we can give this value to node 2, right? This will be removed and 1 will be added here. That now whenever I will consider this node 2, I will not consider its value as 6. Instead, I will consider its value as 7, because this node has considered a value of 1 to node 2, right? Now the next node was this node 5. Its value is 2, not divisible by k. So this will also not form a valid component within itself. So this will also give its value to node 2, right? So this will be removed and 2 will be added here, right? Then if you see, this particular node is now having the in degree as 1, because we removed those two nodes, right? We included their contribution here. So this node again is having its in degree as 1, right? But first let's consider these two, right? Because we were considering all the leaf nodes first, and then after removing that, whatever new leaf nodes we are getting, that we will consider, right? So first let's consider these. So 5 alone, not divisible by k, so this will also contribute, right? So it will add its value here, and then this one alone, this will also not contribute. So we'll add a 1 here, right? Now these two nodes are again having their in degrees as 1, right? So we will consider them also. So here if you see, its value is 2 plus 1, 3, and 3 plus 6, 9, which is divisible by k. So then that means this is a valid component, right? And the valid component was node 2 with node 6 and node 5. This is a valid component. So whenever my value is divisible by k, I'll say this is a valid component and I will increase my count by 1, right? And since this is a valid component, this edge will be removed, right? So I can remove this, right? So if you will see again, node 0 is having its in degree as 1, right? So after considering this node, we will consider node 0 as well. Right now we won't consider, right? Because this was identified prior to this node 0, right? So let's see this one. Here it is 0 plus 5 plus 1, which is 6. 6 is divisible by k. So this is also a valid component, right? And the component was this 4 and 3. This was the component, right? So we will increment our count by 1 and this will be removed now. The edge will be removed, right? And now we are left with this node 0. Its value is 3, which is divisible by k. We will increment our count by 1 and this is our answer, right? So see, this node 0 was not considered twice because when it had its in degree as 1, at that time we considered it. So now when it's in degree 0, we won't consider it again. We will consider it only once, right? So see, what did we do? So first we considered all the leaf nodes, right? Then we considered the new leaf nodes and then the new leaf nodes and so on, right? So can I say that I'm kind of going layer by layer, right? First I checked for this layer, then this layer, and then this layer, right? Kind of. In this particular case, I'm doing it, right? So can I say that I can apply a BFS over here? Right? Because I'm going layer by layer. But instead of starting here, I will start with the leaf nodes, right? And also since it is an undirected tree, then it is not mandatory that node 0 is the only root. Node 2 is also the root of our tree. Node 6 is also a root of our tree, right? Because this is not a binary tree. This is just an undirected tree, right? Any node can have any number of childs or neighbors. Since this is undirected tree, we will say neighbors and not childs, right? So any node can be the root node, right? So what we will do is that we will follow the BFS approach while considering all those nodes one by one, which are having their in degrees as 1, right? So what you can do is that from this edges, right? First you will create an adjacency list, right? That okay, node 0 is connected to node 1 and 2. Node 1 is connected to 0, 4 and 3. Node 2 is connected to 0, 5 and 6. Node 3 is connected to 1. 4 is connected to 1. 5 is connected to 2 and 6 is connected to 2. This will be our adjacency list, right? Then you will create an in degrees vector, right? So that will be 0, 1, 2, 3, 4, 5 and 6. And what all will be the in degrees? So for 0, it will be 2. For 1, it will be 3. For 2, it will be 3. For 3, it will be 1, 1, 1, 1. Right? So these will be the in degrees. Right? Now, what you will do? What do we do in a BFS? We take a queue. Right? So in that queue, first we will push all the nodes where the in degree is 1. So that will be node 3, 4, 5 and 6. Right? So in our queue, we will store node 3, 4, 5 and 6, right? Now we will start our BFS that while our queue is not empty, we will take the front node, which is node 3, right? So we will check that for node 3, what is the value? It is 1, right? Basically, this will be removed. So its value is 1. Then we will see that this is not divisible by k, right? So this alone will not be able to create a component, right? So it will contribute to its neighbor, right? So we will check that what are the neighbors of 3, right? So there is only one neighbor of 3, that is 1, right? Its in degree right now is 3, right? So what we will do is we will add its value in this, right? So basically there will also be a vector like this values where you will be maintaining these values. So in these values for node 1 we will add this value 1, right? So this will become 1, right? And now since we are not considering this, so this edge we should not consider, right? Basically the in degree of 1 now should be decremented by 1, right? So this will become 2, right? And then we will do same process for 4 and 5 and 6 and we will update the values as well as the in degrees, right? So once we will be done with this, then we will consider node 2 and node 1, right? Because they will be our new leaf nodes or the new nodes which are having their in degrees as 1, right? So now when you will be considering them, at that time you will be having node 2 and 1, and at that time their in degree will be 1 and 1, right? So now when you will see that for this the sum is divisible by 3. Its sum was coming out as 6 plus 1 plus 2, which was 9. So this was divisible by 3, right? So we will remove this. We will count our component, right? We will increase our number of components by 1. But now since this component has been considered, the in degree of its neighbor should be decremented by 1, right? So whether it is a valid component or not, in both of the cases the in degrees of its neighbors has to be decremented by 1, right? So this will become 1. And now we will see that node 0's in degree is 1. So we will push node 0 inside our queue, right? And then since this was a valid component, so in node 0, we won't be adding anything into its value, right? And then we will check for this node 1. So node 1 will come out and we will see what was the sum at node 1. So it would be the sum of these, which will be 5 plus 1, that is 6. That is divisible by k. So we will increase our number of components by 1, and this will not contribute anything to the value of node 0, right? And since we have considered this, so the in degree of node 0 will be decremented by 1 again, and it will become 0, right? So now in the queue, we will be inserting a node only when its in degree is 1, right? So now it has become 0, so that is why node 0 won't be pushed again into this queue, right? So now we'll check for node 0. Its value will be 3, which is valid. We will increase our count by 1, the count of number of components by 1, and our queue will become empty, and then we can stop there, and our answer will be the number of components that we have counted, right? So let's quickly look at the code to understand what are we trying to do. So first of all, let's put a base condition that if n is less than 2, basically if there are zero number of nodes or if there is only one node, right? In that case, the number of components will always be 1, right? So that is our base condition. Then let's define our variables. So first will be our answer, right? Which will tell us that how many number of components we have created. Then let's create a vector of vector, which will be nothing but the adjacency list, right? So let's name it G, denoting a graph. Its size will be equal to the number of nodes, right? Then let's create a vector for storing the in degrees of the nodes, right? Its length will also be equal to the number of nodes, and initially all the values will be 0, right? Then what we need to do, we need to update our in degrees and the adjacency list, right? So we will run a for loop that for auto edge in edges, the node 1 will be edge of 0 and node 2 will be edge of 1, right? Then in the adjacency list at node 1, we will push back node 2, right? And in the adjacency list at node 2, we will push back node 1. Because it is an undirected tree, that is the reason that we are pushing in both the nodes, right? So in node 1, we are pushing node 2. In node 2, we are pushing node 1, right? And since this is undirected, we will have to increase the in degree of both the nodes by 1, right? So the in degree of node 1 will be incremented by 1, and the in degree of node 2 will also be incremented by 1, right? Now, before starting our BFS, let's see, this values vector is an integer, right? And you saw that in our BFS, whenever a node is not able to create a component, it will give its value to its neighbor, right? So we will be basically adding the values, right? And these values can be very large, and when you will be adding those values, they will overflow the range of integers, right? So what we can do is, we will create another vector and its type will be long, right? Let's name it long values, right? Now in this, we will store our values vector, right? Values dot begin, values dot end, right? So we just created a long vector out of this vector, so that in this long, we can add the values of the nodes without having the error of integer overflow. Right now, let's create a queue for our BFS. It will store an integer, right? We will be basically storing the node index 0, 1, 2, 3, right? We have named it queue. Then first, we will be inserting all the nodes into the queue, which are leaf nodes, basically whose in degree is 1, right? So we'll run a for loop of I starting from 0 till n, I plus plus. Inside this, we will check that if the in degree of I is equals to 1, then push I into the queue, right? So once we are done with this, we will start our BFS, that while our queue is not empty, what do? We take the front value, right? So which will be current, it will be q dot front, and we will pop it, so q dot pop, right? So once we have got this, what we need to do? We need to decrement its in degree by 1, right? So we will decrement the in degree of current by 1, right? Then we will see that what is the value that it is going to add in its neighbors. If the value of current is divisible by k, then nothing will be added. Otherwise, whatever is the value of current, that will be added to its neighbor, right? So let's create a variable of type long. Let's name it carry, right? Now in this, we need to check that if the value which is present at cur, is it divisible by k or not. So we will check in the long values vector that if this value is divisible by k, right? In that case, nothing will be added to the neighbors, right? So we will give 0. Otherwise, whatever is its value, that will be added to the neighbors, right? So we will give that value, right? Now, if this carry is 0, then that means its value was divisible by k and nothing is going to be added to the neighbors. Then that means this is one of the valid components, right? So I should increase my answer by 1, right? And now when I'm done with this, now I should consider all the neighboring nodes of my current nodes, right? So I will run a for loop for all the neighbors, right? So int neighbors ng in the list we have created, right? That is G. The name was G. So in the adjacency list of the current node, right, we will take all its neighbors. We will check that if the in degree of the neighbor is greater than 0, right, in that case we will decrement its in degree by 1, right? We saw that whether this current node is a valid component or it is not a valid component, in both the cases we will be removing the edge from its neighbor to that node, right? That is why we are decrementing the in degree of its neighbor by 1, right? And then in its value, in the value of the neighbor, we will add the carry, right? So if it was a valid component, then nothing will get added, that is 0. Otherwise, the value of the current node will be added in the neighbor, right? And then we will check that if the in degree of node has become equals to 1, then let's push it inside our queue, right? So in the queue, we will push the neighbor. That's it. We can just at the end return our answer, right? So this is what we needed to do. This is kind of a BFS that we have applied over here. So let's run this. So now in this particular case, if you will see that this loop is running for all the edges, right? And if we consider the number of edges as m, so we can say that this loop is running m times, right? Then here in the log values, we are inserting all the values, right? So values vectors length is n. So this will take order of n time. And then here again, we are running a loop n times, right? Then we are performing BFS over here. Now this BFS will consider each node exactly once, right? And here when we are considering this neighbor, see, we are not adding to the time complexity here. Each node will be considered only 2 times. So for example, if I have a node 0 and node 2 connected with each other. So once I will visit node 2 when I'm considering node 0, and when I'm considering node, then I will consider node 0, right? So basically I will be considering each node only 2 times, right? So we can say that this will take order of n time, right? So we can say that the overall time complexity of this code will be n plus m, right? And coming towards the space complexity, so here we have taken a vector for adjacency list of size n and it will be storing all the edges, right? So we can say that it will be taking order of m space, right? Then an in degree vector which will be of size n taking n space. Then this long values vector will again take n space, and then this queue for BFS. So in the worst case, when all the nodes are leaf nodes, right? So in that case, the BFS queue will store all the n nodes, right? So this will also take n space in worst case, right? So we can say that the space complexity will also be order of n plus m. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.